He has a bad.
You are ready? Can you start? Yeah, can you unmute and come on the camera for some minute, and then or you are already sharing your screen, right?
Screening is right.
Yeah, you have to unmute.
No. Yeah. Yeah. All right. Yeah. Thanks.
Hello, good afternoon, everybody. We are starting this session with a talk by Dr. Venky Krishnan. I'm happy to introduce my colleague, former colleague. I'm former retired from KFR. He's here for Center Bangalore. He works on inverse problems and integral geometry at PDE and several related things. And today he is going to talk about higher order Reshetnyak formulas for the rate transform of symmetric tensor fields in Sobolev spaces. So yes, Venky, the stage is yours.
Yeah, thank you very much, Maithili. And so before I begin, I apologize for the delay. I was actually waiting in the other Zoom room, but apparently that was not the correct Zoom room. So I sincerely apologize for keeping you waiting. So I have 30 minutes, right, Maithili? So let me begin. So this is the title is Reshetnyak formulas for rate transform of symmetric tensor fields. And before I begin, this is joint work with Professor Vladimir Sharafidinov of Sobolev Institute of Mathematics, Russia. Yes. Some acknowledgements are due, of course. So I would like to sincerely thank Professor Vijay Thomas, Professor Nila Nataraj, Professor Sudhir Gorpade, and of course, Professor Maithili Ramaswamy for the very kind invitation, and of course, the other organizers. So it's a great honor to be able to give a talk at this fourth BRICS conference. Okay, so the overview that I'm actually going to follow is, so first we will start with the Radon transform. So this is actually well known. But the Reshetnyak formulas, which I will actually explain quickly, what we mean by that. So that has been known only very recently, and then we will get to rate transform of functions, and then we will get to the main topic of this talk, which is rate transform of symmetric tensor fields. Okay, so first let me go to the Radon transform. So the definition of the Radon transform. So this is you take a function, and then you so the Radon transform is defined as integrals of f along hyperplanes. So the hyperplanes are parameterized by the unit vector which is perpendicular, or a unit vector which is perpendicular to the hyperplane, and p is the signed distance from the origin. So note that C comma P, if you parameterize the hyperplane, then minus C comma minus P also parameterizes the same hyperplane. So there is some evenness condition, so that we will come to later on. So other than that, the C comma P is, it actually uniquely defines a hyperplane. Okay, so the original Reshetnyak formula, or it's actually a Plancherel-type formula, similar to the Plancherel relation that you might have come across in your Fourier analysis course. So this was actually proved by Reshetnyak in the 1960s, and Helgason also gives a proof in his book, The Radon Transform. So basically what it does is the following. So you take F and then you take RF and then you apply some kind of differential operator or a pseudo differential operator. Then that extends to an isometry from L2 of Rn to L2 of even functions on Sn minus 1 cross R. So this evenness is because of the reason that I just mentioned, that C comma P and minus C comma minus P, they define the same plane. Okay, so what is this operator? So I use the box operator over here. So this is not to be confused with the wave equation. So the wave equation does not come. There is a relation between Radon transform and the wave equation. But the box here only, actually I'm only going to use it in this particular slide. It is actually this particular operator, which, okay, for certain things it's going to be a differential operator, but in general it's going to be a pseudo differential operator. And so one thing that I want to emphasize is that the Fourier transform, the RF, the hat denotes the Fourier transform. The Fourier transform is only taken in the P variable. So in this P variable, so C is actually just a parameter. And sorry. So then what we have is, so going from the first line to the second line, it's what is called as this Fourier slice theorem. I'll come to that in just a second. So then what we have is, so this is the original Reshetnyak formula is an isometry relation between L2 and L2 of even functions on Sn minus 1 cross R. Okay, so then what we want to do is we want to do this for Sobolev spaces. So in this context, a modified Sobolev space was introduced by Professor Vladimir Sharafidinov, and so it is defined as follows. So it is the usual Sobolev space HS of Rn, but it behaves, the frequencies, depending on whether the frequencies are large or small, there is a different asymptotic behavior. So for instance, if you take t is equal to 0, then that's just the standard Sobolev space, right? And but what we want to do is we want to have different behavior at infinity compared to the origin. So it is in that context that so Sharafidinov actually defined this Hilbert space, which is a completion of the Schwartz class functions with respect to this particular norm. And similarly, for functions on Sn minus 1 cross R, for instance, for the case of Radon transform, so it's exactly the same expression, except that now you only take the Fourier transform, as I mentioned, with respect to the S variable, and with respect to the C variable, it's just an integration. And one thing that I want to emphasize is the following. Is that you take t to be bigger than minus n by 2 for the case of HST of Rn, or t bigger than minus half for the case of, in order to define HST in of Sn minus 1 cross R, because you want to have integrability near the origin. Okay, so this is what I just mentioned, that for the case of t is equal to 0, these two spaces coincide. And yeah, the important point is that the weights, they have the same asymptotic behavior at infinity, right? So mod y to the 2t and 1 plus mod y squared to the s minus t compared to 1 plus mod y squared to the s. So they have the same asymptotic behavior at infinity, whereas they behave differently near 0, these two weights. Okay, so if t is bigger than 0, then we actually call this as the Sobolev norm with attenuated low frequencies. And if t is less than 0, then we call this as the Sobolev norm with amplified low frequencies. Now, I'm not going to go too much into this, but some care should be taken in dealing with these HST spaces because these are not spaces of distributions. The reason, okay, one motivation being that near zero, you can have functions which actually blow up, or correspondingly, the thing is which can actually, 1 plus 1 by the function. Let's say you have a function which is like a reciprocal, and then that actually, the behavior near the origin can be controlled by taking these t to be quite big. So these are not necessarily spaces of distributions. So some care should be taken. And one way to think of this is you always look at this HST as a completion of S of Rn with respect to this particular norm. Okay, so now let me get to this. So this was the original or the Reshetnyak formula for the Radon transform. This was proved by Sharafudinov. So which is that FHST of Rn is the same as Rf with respect to this particular. So this is the weighted Sobolev, the modified Sobolev norm. Now, for the case of S is equal to 0 and T is equal to 0, so this actually goes back to the Reshetnyak formula, the Plancherel-type formula of Reshetnyak from the 1960s. Actually, the proof for this is actually quite simple, that this FHST is equal to Rf with respect to this particular norm. So this is actually quite simple. So let me actually show this to you. So for this, what we have to do is we just have to use one relation, which is called as a Fourier slice theorem. And so the Fourier slice theorem is actually quite easy to prove. You just take the Fourier transform, and then you just need to apply the Fubini theorem. So I'm not going to prove the Fourier slice theorem, but let's just take this particular formula for granted. And if we have this, then what we have is, so now let's substitute this back over here into this particular. So I'm just using the relation, the formula for Rf with respect to this particular norm. And in here, in Rf hat, I substitute this Fourier slice theorem. But one thing to observe here is that, so now I want to change into polar coordinates. But one thing to observe is that I'm going to use the evenness. So Rf is even with respect to Q, C. Therefore, the Fourier transform also is. And so once I observe that, then what I have is that this can be written as the integral from 0 to infinity instead of integral over R. And now I use this the Fourier slice theorem, and that gets me to the next step. And now the procedure is clear. Now all that I need to do is just substitute QC is equal to Y, and then I come back to polar coordinates, and that n-1 goes away because that's the change of variable formula between Euclidean and polar coordinates, and that's exactly what I have. So why are Reshetnyak formulas important? So the Reshetnyak formulas are important because they give the best stability estimates for the inverse problem of recovering a function f from the Radon transform. And so I want to explain with a view towards going to higher order Reshetnyak formulas. So this is an important point. Now the manifold, if I look at the manifold Sn-1 cross R, so this consists of these two pairs, right? And the variables C and P, they are of different natures. This is like so one can think of this as an anisotropic Sobolev space in which you have certain the derivatives, the partial derivatives are not the same compared to which direction that you consider, right? So people have studied such anisotropic Sobolev spaces. So this is one such example of an anisotropic Sobolev space. So there is some kind of anisotropy, and this is one of the motivations for defining these type of weighted Sobolev spaces. Now, so for an integer, this is just an example. So for an integer, suppose you take S to be an integer, then the space HS. So this consists of L2 integrable functions of order less than or equal to x only with respect to the p variable, because the Fourier transform is only taken with respect to the p variable. The C parameter, which is on the sphere, is just a parameter. Okay. Now, because by our definition of HST, right, we are only integrating with respect to the C variable. So, so what we have is we just have only L2 integrability. And it is for this particular reason that we actually call this as the zeroth order Reshetnyak formula, because I want to consider higher order Reshetnyak formulas. So the term zeroth order means, in this case, the absence of derivatives with respect to the C variable. Now what we want to do is we want to consider higher order Reshetnyak formulas. So which means that we also have to consider derivatives with respect to the C variable. And so this has also been studied. In fact, it was studied in a very recent paper in the context of Radon transform by Sharafudinov himself. And so actually in this, so I'm actually going to quickly go over this because I want to come to the ray transform case. So the higher order Reshetnyak formulas, which corresponds to derivatives in the C variable, is done using the spherical Laplacian. And the spherical Laplacian, so this, and then the Sobolev space with respect to the Sobolev norm with respect to the spherical Laplacian is given here as follows. And then what you do is you consider the spherical harmonics and use the spherical harmonics to actually derive higher order Reshetnyak formulas, or in other words, stability estimates relating F and RF, but in higher, more regular Sobolev spaces, with especially with regard to derivatives in the C variable. Now the derivatives in the C variable is accomplished using this spherical Laplacian. So let me just quickly go over this. So so what you have is, using the spherical harmonics expansion, here this expansion, the last displayed equation, that expansion. So one can actually define an analog of the higher order Sobolev norms. Especially, so now you see that you have this HRST. R denotes more. You can think of it as more derivatives in the C variable, the angular variable, and so you define this as the HRST norm. And analogously, we can also define the HRST of Sn-1 cross R norm. And then by the way things are set up, so what you actually have is equality. So therefore, so this is actually the theorem that Sharafudinov proved, that if you define these Sobolev spaces, HRST using the spherical Laplacian and HR S tilde T tilde of on the Sn-1 cross R manifold, then you actually have an isometry relation. So that is, the norms are norm of F is the same with respect to this HRST norm is the same as norm of RF with respect to that HR S plus n-1/2 T plus n-1/2. Now, one thing that I want to emphasize is that because there is an integration involved, so there is actually smoothing. There is a smoothing effect, and that smoothing effect is actually is the motive, or it shows up in the fact that you actually have that the order of SNT increases by the same order, n-1/2. Okay, now what I want to do is I want to come to ray transform of functions. So these has also been studied, and the zeroth order Reshetnyak formula has also been proved, as the first order Reshetnyak formula also has been proved. So these were done by Sharafudinov in recent works. So I want to give a motivation for that, and then we will get to the main topic, which is a ray transform of symmetric tensor fields. Okay, so in the case of Radon transform, it was integral of F along hyperplanes, and now what we want to do is we want to consider ray transform of functions. We want to consider line transform of that is integral of F along lines in Rn. So the lines can be parameterized by the tangent space to Sn-1 for the following reason, that suppose I give you a C, then you consider the plane which is perpendicular to C passing through the origin. So that's going to be the tangent space to Sn-1. So now you can have a starting point on that particular plane, and the line is parameterized by that starting point and the direction C. So therefore the line, so given the point x comma c, I have x plus tc. So that's going to be the line. right? Now, obviously, the thing is you can actually translate along the line, and that's going to define the same, it's going to parameterize the same line. But then, the starting point is now going to be different. So therefore, if you specify that the starting point is actually along the plane which is passing through the origin, so then this gives you a well-defined parameterization. Okay, so now what we want to do is initially we study for functions only, but with a view towards studying for symmetric tensor fields. So I want to consider the rate transform of symmetric tensor fields. So suppose you to consider a symmetric tensor field, which is f, which is indicated by f I1, I2 up to Im. Now by symmetric, I mean that you do any permutation of these indices f of these I1, I1, I2 up to Im, then that's going to give you the same. So there is a symmetry, and so then you define the rate transform as the last displayed equation. Okay, all right. So now what we want to do is, so similar to what we did for the Radon transform. So there is a connection between the Fourier transform and the Radon transform. But in order to define the Fourier transform, so you see that so this is the usual Fourier transform of function, and for tensor fields you just do it component wise. Now I need to tell you how do you define the Fourier transform of a function on Tsn minus 1, right? So in this case, what you do is, now C is a parameter, so you actually consider the n minus 1 dimensional Fourier transform along the plane which is perpendicular to C. So that's the reason why you have this C perp over here. So it's an n minus 1 dimensional Fourier transform. So that's also one more reason why we put this n minus 1 by 2 instead of n by 2. Okay. So in other words, it's a standard Fourier transform, but in the one dimension less space. And analogous to the Fourier slice theorem. So there is actually, so this can be viewed as the Fourier slice theorem for rate transform. So if you consider if hat of y comma c, so that's going to be up to a constant f hat cm. So this is f hat, this bracket is given by, it's just an Einstein summation. So f hat I1, I2 up to Im, ci1, ci2 up to cim, right? So in particular for the rate transform of functions, right? So then this is no longer a tensor field, it's just a function. So then you have this nice relation. Okay. All right. So now analogous to the HST spaces on Sn minus 1 cross R. So Sharafudinov in that same paper also defined a non-standard Sobolev norm for functions on Tsn minus 1. So that's given as follows over here. Now it's pretty much the same thing, except one thing to notice is that, so here the Fourier transform, so this is functions on Tsn minus 1 on the tangent bundle to the unit sphere. So it is u hat. So this u hat only denotes that it's a Fourier transform only in the x variable, right? C is just a parameter. Notice that the other thing that I want to mention is that t is greater than minus of n minus 1 by 2. So this is required to actually guarantee integrability. But you have n minus 1 by 2 because of the fact that you have the Fourier transform is actually taken on a one dimension less space. And the HST norm is defined as a completion with respect to the above norm. Okay. So then for the rate transform of functions, Sharafudinov actually proved the following Reshetnyak formula, that if you consider IF in this H S plus half T plus half space, that's going to be up to a constant, the same as F HST. And again, because of the fact that you have an integration involved, so there is some smoothing, and that is reflected in the fact there is actually a half order smoothing, and that's reflected over here. Okay. Now, notice that in the definition of the HST spaces, there is no differentiability in the C variable, right? So for this particular reason, we call this isometry as the zeroth order Reshetnyak formula. Okay. So now what we want to do is we want to define a first order Reshetnyak formula. So just 1 second, let me just check how much time I have. Okay. So we want to define a first order Reshetnyak formula. So in order to do this, I want to consider certain differential operators on Tsn minus 1. Okay. So some vector fields on Tsn minus 1. So these were defined in one of our papers. So this was a paper with Sharafudinov, then a student of mine and a postdoc of mine, a former student and a former postdoc. And so we actually defined this vector field in the context of study of momentum rate transforms. So these vector fields are going to be defined as follows. Sorry. So these vector fields are defined as follows. So this is ddci minus xicp ddxp minus cicp ddcp. And you can think of this as, so if you just look at the leading order term. So the leading order term is going to be ddci, and that kind of denotes differentiability with respect to the xi variable. So I apologize for this phone. There is no way for me to stop it. So yeah, I think now it has stopped. Okay. So these vector fields are tangent to TSN minus 1. So this can actually be viewed as vector fields on TSN minus 1. So with this, Sharafudinov actually proved this in a very recent paper. So he derives a formula for sigma IIF, and that's actually given by this particular, or the so this is the L2 norm, the summation of the L2 norms. So that's actually going to be, it's actually going to be given by this. Notice that one thing that I want to emphasize is that you see that the main relation that is used to actually do this is this particular formula. So it just uses the Fourier slice theorem. And once you use the Fourier slice theorem, so then what you have is, notice that on the left hand side you have IF, whereas on the right hand side it's just something on Rn only and only on F. Right. So this is actually a motivation to define suitable higher order, or in this case, first order Sobolev norms. And that's exactly what Sharafudinov does. So he defines HS1, S, 1. So actually, I'm going to do the opposite order in the later work. But this was how he defined in the original work. So the 1 denotes the first order. Okay. So that's going to be the original F, the HST norm, plus this new term. The new term is motivated by what happens over here. Okay, and then we know how to define. So if this is how we are going to define the HS1 norm, then we just need to give a suitable definition for HS1 of TSN minus 1 norm, and not surprisingly, it's going to be given by this. It's going to be given by this. Now, by the way that we have defined, so then we actually have equality. So therefore, we actually have an isometry relation. So one can think of the main contribution of this particular work is to actually define this analogous HS1. So what are the right spaces to define so that you actually have equality, right? So now now the natural thing is as follows. So okay, so the Sobolev norm, or actually the isometry relation, or the Reshetnyak formula that Sharafudinov proves, is given by this particular theorem over here. This is HS1T of Rn and HS plus half 1 T plus half. Now, one thing that I want to emphasize is the following: that this is actually into, okay, and it's not actually onto. And so the range characterization is actually quite important. Actually, it is precisely for the range characterizations that we actually started looking at these higher order Reshetnyak formulas, or more specifically, this higher order Sobolev spaces. But I'll come to that in just a second. Okay, so this we refer to as the first order Reshetnyak formula, and the natural question is, what about higher order Reshetnyak formulas? So the higher order Reshetnyak formulas. So this is going to be the content of my last part. So let me just recall the definition. So the definition is given as follows. This we saw it already. Now there is a main difference between tensor tomography of functions, which we call as the scalar tomography, and the scalar or the tensor tomography, wherein either vector fields or higher order tensors are involved, in the sense that there is an infinite dimensional kernel. So, for instance, one can actually think of so let's consider for the case of a vector field. So, suppose you take a vector field, suppose you take a function, which is, let's say, CC infinity, and then you take the gradient of that function. So, the gradient of the function is now going to be a vector field, And because you have CC infinity, integral along any line is going to be 0 just by fundamental theorem of calculus. So this is one, this is infinite dimensional. So you have this infinite dimensional kernels to worry about, and that's actually the main difficulty in dealing with functions compared to vector fields or tensor fields or any of those objects. Okay, so it is for this particular reason that we actually have to restrict ourselves to certain subspaces of the Schwartz class functions with values in symmetric tensor fields. So the natural candidate is what are called as the solenoidal tensor fields. So the solenoidal tensor fields are which are divergence free. Okay, so I actually have it in the later slide. So let me just move on. So I have very little time now. So let me actually tell you what the motivation is. So the motivation for this comes from the motivation that was defined for in order to define for the Radon transform. For the Radon transform, we actually use the spherical Laplacian. So we want to define an analogous thing over here, and the analogous thing that to look for is actually this version of the Laplacian, which is delta xc, using the tangential vector fields which was defined earlier, which is sigma I square. But there is actually a difficulty. The difficulty is here that this particular operator it's not positive definite. This is only positive semi-definite. Okay, so it is for this particular reason that we are actually not able to give this HRST definition for R being any real number. We are only able to do this for positive integers. So now, once we have this, so then we define the norm, the HRST norm, as so analogous to what we did for the Radon. Okay, not what we did, what Sharafudinov did for the Radon transform, which is identity plus. So in that case, it was a spherical Laplacian. So now we have delta xc raised to R, where R is now an integer. Okay, and then we define HRST norm as a completion of the Schwartz class functions with respect to this norm. So now the HRST norm actually can be defined. So one can actually show that it can be written in the following form. Now, one thing that I want to emphasize here is the following: that this inner product here is with respect to the induced Riemannian metric on Sn minus 1 from the standard Riemannian the Euclidean metric on the ambient space. So this was this is crucial for a lot of calculations. If you were to do this without that, actually the calculations, so this was our primary insight, that the right way to look at it is in terms of the covariant derivatives, not actually the usual derivatives. So the usual derivatives actually give problems. If you look at covariant derivatives with respect to the Riemannian metric, the standard Riemannian metric on the sphere, then actually it leads to a lot of simplifications. Now, the solenoidal tensor fields that I just mentioned are the divergence free. So the divergence free tensor fields are given over here. So DFP, XP. So you fix any of the indices, you fix I2 up to IM. So it actually goes into one dimension, one rank less tensor field, symmetric tensor field. Okay, so then the HRST norm can be written in the following form. It's just basically, so I have not done anything fancy. It is going from this particular formula and then using this relation to actually get this formula. And then this is our main theorem, that the HRST, so we have the rth order Reshetnyak formula relating, sorry, I defined it over here. Yes. So I defined this IF, sorry, I forgot to mention this. So we define this IF R HS R S plus half T plus half, and again there is a half order smoothing on this tangent space as this particular. So using this equality, we actually define using this equality we define the norm, and by the way that we have defined the norm, we actually have equality. Now notice that one thing to keep in mind is the following, that analogous to what what Sharafudinov did for the case of functions, you see that on the left hand side, right, you have something involving I, And on the right hand side, you have something involving, okay, it's essentially it's integral over Rn, right? Involving F only. So that's the motivation to actually define the suitable HRST norms on Rn and HRST norms on TSN minus 1. And so if you define the norm using this relation, so then we actually have equality by the way that we have defined. Now, so what was our motivation to actually define this HRST norms? As I mentioned, our main motivation was range characterization. Now, the range characterization, if you are familiar with it, so in in dimensions 3 and higher, there are these John operators. So this was actually first proved by Fritz John, and this has been extended to any so for instance, what would be the characterization of the range of I? Now, our primary motivation was to actually consider range characterization of I acting on Sobolev spaces. So because you have, so what is a John operator? So the John operator you fix two indices I and j, then you have ddxi or d square xi ddcj minus d square xj ddci. So notice that you have this ddci, that derivative. So in order to consider this ddci, we have to actually consider derivatives with respect to the C variable. So that was our motivation to actually define these higher order Sobolev spaces. And so we have the Reshetnyak formula and the range characterization. It's actually, we are working on it. So that's it will be a topic of the forthcoming work. So I thank you very much for your attention, and I'm sorry I went a bit over.
Any questions?
Yes.
I have seen some problem for the function which is defined on Sn minus 1. So you are trying to get Fourier transform on that.
Sorry, just 1 second. Let me turn the fan off over here. I'm not able to hear you well. Just 1 second. Yes, sorry. Can you please repeat the question?
Yes. You see, for a function which is defined on Sn minus 1, then how to define Fourier transform of that? You
Okay, so
something that you maybe correctly understand it to go in the direction of the normal.
okay, so we actually define, okay, let me just go back to that particular, this one. So we actually define the Fourier transform only in the P variable. So you have this RF of C comma P, right? Now in P, it's, so you fix C. So C is fixed for the discussion and only P you consider. So in the P, it's just a function of R. So it's a one-dimensional Fourier transform only in the P variable. So with respect to C, it's just a parameter.
I consider it as this. Okay.
Yeah, did I answer your question?
Oh yeah, yes.
Yes. Okay, thank you.
Just one quick question to Venky, that you characterize the range of I by is that the other Sobolev space which appears on the right hand side?
Characterize the range of I. Yes. So you mean for functions, yeah? I acting on functions, is that what you asked, Maitli?
Yes.
Yeah, it can be done. So basically what you have is so you will have you will have two so it's going to be a John operator, right? So this is only dimensions n bigger than or equal to 3. So you will have the John operator, so involving the John operator. So the range can be characterized. And what we want to do is we want to do it also for vector fields and tensor fields and things like that.
Okay, so if that is now you are able to do or you are working on it.
So we are able to do it for vector fields, right? And the higher order objects, you know, that is for symmetric tensor fields and things like that, we have not quite finalized the work yet. So just to go back to your point, right? So suppose you consider, let's say, the ray transform, and then you apply, let's say, ddxi, ddcj minus ddxj, ddci, and that's going to be equal to 0, right? So what Fritz John proved is that this is also, it's a both necessary and sufficient condition. So in dimensions n bigger than or equal to 3. In dimensions n is equal to 2, it's going to be different. It's going to involve integral conditions. So these are what are called as the moment conditions, because it's in dimension 2, the ray transform and the radon transform are essentially equivalent up to a parameterization. So therefore, you actually have integral conditions, not differential conditions. Now, in the case of ray transform, in the case of functions, it's already done in the Sobolev space. Actually, this was done by Sharafudinov. And what we want to do is we want to do it for vector fields and tensor fields and things like that. It was so we haven't quite finalized the work yet, but it's nearly done.
Okay, thank you. Thank you.
Yeah, thanks, Maitli. Thank you very much. I'll stop sharing now. Thanks.